Without further ado, let me introduce the next talk. It will be EMD, Fair and Efficient Dynamic Memory De-bloating of Transparent Huge Pages. And the authors are Parth Gangar, Ashish Panwar, and Gopinath. And they're from Fujitsu Research, Microsoft Research, and Rishihood University in India, respectively.
Hello everyone, I am Parth Gangar and today I'll be discussing my work on efficient memory de-bloating or EMD, a system designed for fair and efficient dynamic memory de-bloating of transparent huge pages. Now this slide outlines the structure of my presentation. I'll start with a brief introduction to virtual memory and huge pages. Next, I'll discuss the motivation, specifically focusing on the need for fair and efficient dynamic memory de-bloating in operating systems. Following that, I'll delve into the design of our proposed solution EMD. We'll then move on to the evaluation phase, where I'll present results that demonstrate how EMD improves fairness and efficiency compared to existing solutions. Finally, I'll conclude with some closing remarks. Now, virtual memory is essential in modern computing where the software accesses memory through virtual addresses that must be translated into physical addresses. As memory demands surge with big data workloads, physical memory has expanded from a few megabytes to gigabytes and now to terabytes. Now these workloads require fast access to vast amounts of memory, making efficient address translation crucial for efficient memory access and overall computing performance. To accelerate this virtual to physical address translation, processors cache recently used addresses in multi-level hardware structures called translation look-aside buffers, TLBs. A miss in the TLB can take several memory accesses and may incur hundreds of cycles to service. As memory capacity grows, deeper page tables add another level of memory access, further increasing the cost of a miss. Now, in a virtualized environment, a TLB miss may require up to 24 memory accesses. Unfortunately, while physical memory capacity has grown exponentially, the size of the TLB has barely scaled over the decades. Now, increased memory consumption, deeper page tables, and limited TLB growth, they lead to a phenomena known as the address translation wall, where the memory management unit spends a significant number of cycles translating virtual addresses to physical addresses. Now here is a graph showing percentage of CPU cycles spent in page table walks by various Google data center workloads. As you can see, 9 to 38% of total CPU cycles are dedicated to page table walks alone. To mitigate the cost of virtual to physical address translation, modern processors support huge pages. A huge page enables the hardware to map a much larger fraction of virtual address space into physical memory via a single TLB entry. Huge pages increases TLB coverage, which in turn reduces the frequency of TLB misses. Here is a graph showing the performance benefits of huge pages over base pages. For all these workloads, we observe at least a 60% performance improvement over using base pages. An important note is that in this context, we are discussing transparent huge pages, a technique where the operating system automatically allocates huge pages without user intervention or application level code changes. In Linux, this mechanism is known as Linux THP. Now, while huge pages improve performance, they introduce new memory management challenges. Here are the main issues many workloads encounter when using transparent huge pages, although several research efforts have addressed these challenges. Memory bloat remains a significant problem that no prior work has fully solved. Our work specifically tackles this issue, aiming to effectively eliminate memory bloat. Now, this is the graph we saw earlier showing the performance benefits of huge pages for these workloads. Now, below is the table that illustrates the memory overhead associated with using huge pages. As you can see, for all these workloads, the use of huge pages increases the memory footprint. Now, these observations highlight an important trade-off. Performance can be optimized at the expense of extra memory. Ideally, this trade-off should be effectively managed by the operating system. However, we find that current systems either lack support for managing memory bloat or are not efficient at it. Next, we'll discuss what is memory bloat and what is de-bloating. Now, memory bloat occurs when an application uses more physical memory than necessary due to the allocation of huge pages. For example, if an application accesses just 1 byte of virtual memory, allocating it with a 2 MB huge page results in more memory waste compared to a 4 KB page. Now, this waste occurs because with sparse access patterns, the entire huge page often remains unused, leading to unnecessary memory bloat. Now, Linux THP primarily supports huge pages for anonymous memory mappings, which the kernel initially zero fills. Now, this is an important characteristic which allows for automatic recovery of memory bloat under pressure. Now, de-bloating is the process of reclaiming these zero-filled pages from a process. During de-bloating, the huge page is broken down into its constituent base pages, and the zero-filled base pages are deduplicated into a single zero-filled physical memory page. Now, next we will see how existing systems deal with memory bloat. Linux is both greedy and aggressive in its memory management. It employs a first touch policy for huge page allocation, where physical huge pages are allocated upon the first page fault. While this approach helps reduce TLP misses, it does so at the cost of reserving entire regions of memory for processes that may use less than a full huge page, leading to memory bloat. Now, Engines is a work in OSDI 2016 which promotes huge pages asynchronously using conservative utilization threshold parameter for huge page allocation to prevent memory bloat. Now, FreeBSD is an operating system used in many modern servers, desktops, and embedded platforms. FreeBSD supports transparent huge pages using reservation-based huge page allocation. Now, Engines and FreeBSD huge pages are only promoted after a certain threshold number of base pages have been used. Now, thus, these strategies help prevent memory bloat, but result in an increased number of TLB misses. Hawkeye, which is a research work in ASPLOS 2019, promotes huge pages on the first page fault. It introduces a dynamic memory de-bloating mechanism under memory pressure to balance the trade-off between memory efficiency and performance. Next, we will see why Hawkeye is suboptimal and unfair. To illustrate why Hawkeye is suboptimal, we performed an experiment with a synthetic micro-benchmark that demonstrates uneven memory bloat. The graph on this slide shows that memory bloat is low in the first half of the address space and high in the second half. Now, we used Hawkeye to de-bloat 25% of the memory and compared its performance to a no de-bloating scenario. By de-bloating 25%, we mean that if an application uses 8 GB of memory, we reclaim 2 GB of zero-filled pages. We found that Hawkeye resulted in a 74% slowdown compared to no de-bloating. Hawkeye addresses memory bloat by scanning the address space sequentially and breaking huge pages if they contain zero-filled base pages. However, this approach is not very efficient because it overlooks the crucial fact that memory bloat is different in different parts of the address space. In our experiment, Hawkeye had to break 2/3 of the total allocated huge pages to reduce memory bloat, leading to a situation where there are more base pages than huge pages. As a result, the performance benefits of huge pages are negated. To demonstrate the lack of fairness in Hawkeye, we ran 2 identical instances of the B-tree workload simultaneously and compared their performance under Hawkeye. We conducted the same experiment with memcached as well. To distinguish between different instances of the same workload, we labeled them according to their process creation order. For example, instance 1 represents the first instance 2 represents the second instance of the same workload. As shown in the table, Hawkeye's unfair reclamation policy disproportionately affects the instances. For B-tree, Hawkeye breaks over 19,000 huge pages in instance 1, but only 1,300 in instance 2, a 14.6x difference. Similarly, for memcached, the difference is 4.7x. Now, this imbalance occurs because Hawkeye debloats memory from another instance only after fully debloating the current one, leading to uneven performance impacts. For B-tree, instance 1 experiences a 28% slowdown compared to no debloating, while instance 2 sees only a 2% slowdown. For memcached, the slowdowns are 22% for instance 1 and 4% for instance 2. Now next we'll explain the design of EMD. Now here is the virtual address space of the micro benchmark showing uneven memory bloat distribution. Now this graph, which we saw earlier, represents that uneven distribution. For simplicity, let's divide the address space into 6 huge page candidates labeled H1 to H6. Our approach EMD uses a prioritization scheme for de-bloating memory regions. Each region is de-bloated based on a priority value, which is determined by the number of zero-filled base pages within a huge page. The more zero-filled base pages, the higher the priority value. In this setup, H1 to H3, the first half of the address space, have low memory bloat, thus low priority, while H4 to H6, the second half, have high memory bloat, thus high priority. We use a data structure called the bloat map, which is an array of 10 buckets. Now each bucket represents a different priority value and contains huge page regions with the same priority. So H4, H5 and H6 are placed in high priority buckets, while H1, H2 and H3 go into low priority buckets. As a result, EMD debloats the second half of the address space first before moving on to the first half. EMD's fine-grained approach scans each base page within a huge page. For non-zero filled pages, we skip the base page as soon as we detect the first non-zero byte. However, for zero filled pages, we need to scan the entire base page. Therefore, the scanning overhead depends on the number of zero filled base pages within each huge page. As shown in the graph, the average overhead remains quite low, which is 0.2%. Now, under multi-tenancy, EMD debloats memory regions from the same priority bucket across all processes before moving on to the next bucket. For instance, consider two processes, A and B, launched immediately one after the other. Now, if both processes have memory regions in the same priority bucket, EMD will debloat all regions in that bucket for both processes before moving on to the next bucket. For example, here, A has regions A3 and A5 and B has regions B1 and B6. All of these regions are in the same priority bucket. So EMD will debloat A3, A5, B1 and B6 together before addressing the next priority bucket. Now this approach ensures that regions with the highest bloat are addressed first across all processes, promoting fair memory reclamation. It prevents any single process from being disproportionately affected, thereby achieving a more balanced performance and enhancing overall system efficiency. Thus, the final order of debloating would be B5, A1, A3, B1, A5, B6, B3, B4, A2, A4, B2, A6. Next, we'll move on to the evaluation section. Now, this table outlines the experimental setup used to evaluate our approach. We assessed performance and fairness under three scenarios: single instance workloads, multiple instances of the same workloads, and multiple instances of different workloads. Now we selected a mix of real-world workloads and custom micro benchmarks for our evaluation. Now the figures presented show the bloat distribution across the virtual address space for each of these workloads. For example, B-tree shows no memory bloat for the first 15% of the address space, then experiences a sharp increase to around 90%, which remains consistent for the rest of the address space. Memcached, on the other hand, has memory bloat ranging from 50% to 99% for most of the address space, dropping to 0 towards the end. Random access L and random access R exhibit consisting bloat patterns. Random access L shows low memory bloat in the left half and high bloat in the right half, while random access R has high memory bloat in the left half and low bloat in the right half. We evaluated the impact of debloating on single instance workloads by reclaiming different amounts of memory bloat, such as 20%, 30%, and so on. For example, if an application uses 8 GB of memory and we debloat 20%, we basically reclaim 1.6 GB of zero filled pages. The graph shows the performance impact of Hawkeye, which is in orange, and EMD, which is in green, across 4 workloads: B-tree, Memcached, random access L, and random access R at various debloating levels. We are comparing Hawkeye and EMD against no debloating scenario. Now, as you can see, Hawkeye significantly increases runtime across all debloating levels with an average increase of 1.1x for B-tree and 1.2x for Memcached. In contrast, EMD's fine-grained approach, which considers the bloat distribution across the address space, results in minimal performance impact. For B-tree and Memcached, EMD shows an average runtime increase of less than 1.01x, closely matching the best case runtime. At 50% de-bloating, both Hawkeye and EMD see increased runtimes for the random access micro benchmarks. Now, this happens because over 75% of huge pages are broken during de-bloating, causing the application to rely more on base pages, making its runtime similar to native execution time. For random access L, Hawkeye's average runtime overhead reaches 1.84x, while EMD shows a 1.28x increase, reflecting a 56% improvement. Hawkeye and EMD perform optimally for random access R with an average runtime overhead of 1.28x, since the optimal order for de-bloating in this case is sequential. Now, to understand why EMD outperforms Hawkeye, table shows the number of huge pages broken by both methods at all de-bloating levels. Hawkeye, which de-bloats memory in virtual address space order without considering the varying de-bloat levels, breaks more pages compared to EMD. On average, Hawkeye breaks 6% more huge pages for B-tree, 22% for Memcached, and 41% for random access L. However, the number of huge pages broken by both methods is same for random access R. Thus, EMD outperforms Hawkeye by breaking fewer huge pages and de-bloating memory in a fine-grained manner, thereby minimizing the performance impact. Now, under multi-tenancy, we execute 4 identical instances of B-tree, launching them one after the other with a few seconds of delay in between. The table shows the number of huge pages broken across all 4 instances of B-tree for various de-bloating levels. Hawkeye breaks huge pages one instance at a time based on the process arrival order. It starts de-bloating memory from the first instance and moves on to the next instance only after scanning the address space of the prior one. In contrast, EMD ensures fairness by judiciously breaking huge pages across all instances. It identifies the most bloated regions across all instances and de-bloats them. For example, in the case of 40% of de-bloating, Hawkeye breaks 47% of the huge page from instance 1, 44% from instance 2, and 10% from instance 3. It never de-bloats memory from instance 4. In the same scenario, EMD breaks 27% of huge pages from instance 1, 27% from instance 2, 24% from instance 3, and 23% from instance 4, ensuring fair de-bloating across all instances. Now, before I wrap up, here are 3 key takeaways from this work. Current systems don't efficiently support dynamic memory de-bloating. EMD reclaims memory bloat effectively with minimal performance impact. EMD ensures fairness even in multi-process environments. Our system also requires no hardware or application level changes. Thank you.
All right. Terrific. Yes, terrific. Now, thank you for that talk. I'm the session chair, Steve Blackburn. I'm going to now hand over to questions from the audience.
Sure.
Hi, I'm Tim Harris from OpenAI. I haven't read the paper yet. Thank you for a very nice recording, but maybe this is answered there already. I was wondering what scope there is for taking usage counts into consideration as well as the mapping. So knowing that maybe a huge page has a lot of accesses going through it, even though there's a lot of zeros, and maybe it's best to keep that as a huge page when thinking about the overall performance trade-offs.
Hello, thank you for the question. Firstly, I just wanted to clarify is that you are seeing that the huge page, how is the performance impact when using huge pages? It's better than, let's say, not completely use huge pages. Is that what your question is?
And I was wondering if the reduction in TLB use, if there's a very popular huge page, even if it's inefficient in terms of the amount of non-zero data it contains, is something that's worth retaining.
Yeah, so I have mentioned in the paper. So there is a graph of basically completely not using, only using base pages, and then using EMD with huge pages. So it's like there is a high bloat scenario and there is a low bloat scenario. So you can basically dynamically manage the trade-off. So the difference between completely using base pages and then let's say using huge pages but with EMD, that performance, there is a performance gain in that as well.
Okay. Thank you.
Hi, Eric Eslan from Oracle. I'm wondering if you've considered, rather than de-bloating after the fact, when the bloating has already occurred, potential heuristics for not introducing the bloating in the first place, so that you don't need to de-bloat it, and if there could be some strategies there to also alleviate this pain.
Hey, hi. Thank you for the question. Uh, the thing is that let's say if we have abundant memory, then we are considering de-bloating when there is more memory pressure. If there is no memory pressure, then it's like the workloads, the processes that they can utilize the system resources. But there are ways to manage to reduce the bloat, which are engines and FreeBSD, which I have explained in the presentation. There is also some other works, but they are static based, and they are static based and they are heuristics based.
Okay, I'm looking at the clock, thinking we should finish there. Thank you very much for the talk, and we'll move to the next talk. Thanks.
Thank you.